Balanced input phonostages. Why aren't they the best idea ever? I've been asked a few times this week and the week before as to why there isn't an abundance of phono preamplifiers and why I'm not going to make a phono preamplifier with a balanced input. Now, I do think that in an ideal world, phono preamplifiers should have an XLR 3-pin input, but I don't think it should be balanced, and I'll tell you why at the end. So, what are the benefits of balancing? We can reject common mode noise, we can reject interference, and we can get rid of issues that we might have with ground loops. And ground loops are the bugbear of audio, especially when we're dealing with things like phono preamplifiers and turntables, where we might have a gain of, say, 1,000 times or more at 50 Hertz, the mains frequency, the big problem frequency that we're dealing with in terms of ground loops due to the RIAA curve. So we've got this bass boost and then this cut in the treble. So it sounds like a really, really good idea, doesn't it? But in reality it's not, and I'll explain why. So balanced signalling is really, really useful when we've got two pieces of equipment that are a good deal of distance away from each other. Let's say 2 meters, 5 meters in a professional environment. It might even be 100 meters or so. And those two pieces of equipment are connected to some sort of power safety ground. And so we've got the ground path in the connection between the two units for the signal cable, and then we've also got the power ground that both of these units are connected to. And if we look at that as a circuit, then we can see it's a loop, hence the name, ground loop. And there are loads of ways in which we can have issues with our reference grounds being disturbed by various forms of interference in this system. One way would be if we had some sort of interference current running in our ground path. This is often the case if we've got some sort of mains filtering where the mains filtered out undesirable components, say above 1,000 Hertz or so, are shunted into the safety ground, which is quite common for a lot of mains filters. Or we might just have some magnetic field present, which is very, very common in a home environment or around motors or around transformers. Transformers are a big, big source of magnetic field, especially older ones in equipment where there might be EI core type transformers. They'll just radiate magnetic fields everywhere. And so if they're in proximity to that loop, then we'll get a big current running through that loop. Not big in the grand scheme of things, but big in terms of our small line level signal, which might only be 100 millivolts or so. And so what will happen then is, because the wires in that loop aren't superconductors, they'll have a resistance, and that resistance will convert that noise current into a noise voltage that will be seen effectively as the other end of the connection. And that will add itself onto our signal, and we really, really don't want that. The end result is that horrible buzz that we all know and love. And so a balanced connection, instead of having just one signal wire, we have two. One carries the signal and the other one carries an inverted version of it. So if we're clever and we can design a good amplifier on the other end, which is actually two amplifiers and some sort of comparator that only compares the difference, we don't need to compare the signal to the ground anymore. We just compare the signal to the inverted version of itself and amplify the difference between the two. And by that means we can reject all sorts of unpleasantness that might find its way not only onto the ground path but also onto the two signal wires themselves, as long as it finds its way onto them equally. Fantastic. And so one more way in which we can have issues with ground currents is, even if the source at the other end isn't connected to a ground or a power ground, we can still have issues with noise running through the signal ground path if it acts as a shield. And so a classic example of this might be on a stage microphone, where we might have 100 meters of wire, and that wire will find its way into proximity with all sorts of other cabling that might be carrying mains, that might be carrying some sort of digital control signals, and they'll find their way and capacitively couple onto our ground path, and that results in a ground current which causes a ground voltage, and we get the same problem occurring all over again. But let's consider our turntable. After all, that is what we're talking about here. So the turntable is very much like our microphone, and we have, instead of 100 meters of cabling, we have 1 meter of cabling, and the end is very much open in the same way as our microphone is an open source. There's no power ground at the other end of it. So with our turntable and our moving magnet cartridge, we can't actually have more than about 1 meter or so of cabling coming out of the cartridge, because cartridges are very, very sensitive to cable capacitances. The more capacitance we have, the more the frequency response rolls off in the high end, and it can even peak the response up and cause all sorts of nasty inaccuracies that a lot of people who fiddle around with cartridge loading capacitances are actually looking for, although they're technically not high fidelity and it shouldn't be our goal. But in any case, we can only have that 1 meter of cabling. And so for that reason, there's not really any way in which the electrostatic interference currents that we'd have in our really long length of cabling can get onto our 1 meter or so of interconnect cable. It's actually very, very difficult to get that to happen unless you have to, start moving all sorts of USB cables and things like that into close proximity to your turntable audio output cable directly from the cartridge. So the cartridge is open at one end, and as long as we keep that cable run short, then we never have to worry about ground cable currents. But what about the power ground? After all, our turntable has to be connected to some sort of power source unless it's wind up, and I've yet to see that in the audiophile world, although I'm sure they're going to give it a go at some point. We had battery powered amplifiers. It's only natural that we'll have, wind up gramophones again at some point. But instead of running our turntable ground, the power ground, which might be connected to our tone arm, which might be connected to the mains ground, which might drive our motor, that goes through our separate cable, doesn't it? That's why we have that separate ground cable for our turntable. And so we completely avoid that right off the bat. By separating those two ground paths, we can connect that turntable ground to our reference inside our preamplifier and completely do away with any vestige of interference that it could otherwise impose on that very, very delicate signal coming out of our cartridge, because it's simply not sharing the same ground path with them. And so that's great. So that means that really we don't have to do any balancing if we're careful. But could balancing help things at all? And I think actually no, because like I said, with the balanced input amplifier, you've got to have two amplifier inputs because you're comparing one signal against another inverted version of itself. So you've got two input nodes, and you've also got to have a differential amplifier. And so this is quite a tall order for our moving magnet input because it's high impedance, it's a very small signal, and it's quite prone to noise. So with the standard floating unbalanced version that we currently have with RCA cables, we only need one amplifier input for each one of the cartridge's channel outputs, so just two amplifiers for stereo in total. And that means that we only get the addition of one amplifier's input noise being added onto each one of those outputs. But if we have two amplifier inputs for each channel, then we get twice the noise power. Fortunately, because amplifier input noises aren't correlated, we don't get double the noise voltage. It's actually the square root of 2 multiplied by the noise voltage. But this is still 3 decibels, and nobody, even the most steely-eyed psychoacoustic objectivists, are going to say that you're not going to hear that. And when we look at phonostage input noise compared against, say, the actual physical capabilities of the medium, it's actually about 10 decibels greater than the medium, so we could ostensibly argue that we can measurably degrade the total noise performance of the system by using such a balanced input versus a single-ended one. Not only have we got to have 2 separate amplifier inputs for each channel, but also now we've got to contend with rejecting the common mode element, and that could also add a lot of complexity. You'd have to have the 2 amplifiers bringing the signal up to, say, 10 times what it is at the input, so that the noise performance relative to the next stage is good enough to use a differential stage, and also that differential comparative stage will be quite noisy, and this can be a bit of an issue as well. That's why sometimes you often see, looking at the data sheets and spec sheets of some amplifiers and preamplifiers, that the balanced input is actually noisier than the unbalanced one, which is rather perverse, but unfortunately it's the way that things are. So not only have we got that additional complexity by balancing, but we've also got a noise disadvantage. And that's one of the reasons why you don't see them. It's just simply not necessary. However, of course, there are a few on the market that are coming out and capitalizing on this whole idea of balancing, because it's a very convincing argument at a first glance. Of course, it sounds like exactly what you need, but in reality it isn't. But XLR connectors for phonoamplifier inputs, I'm not sure if I remember, but I did say maybe at the beginning of the video that I was going to say why I think they're better. If I didn't, I'll just cut this bit out, or I just won't bother. But essentially, with our RCA inputs, we've got to have the 2 floating inputs, left and right, and we've also got to have this separate ground path. So that means we've got to have one of those little fly-out wires with a little spade connector on it, and one of those fiddly terminals to deal with. Some are better than others. I mean, I like to use one of those big proper banana plug type screw down terminals that you find on big boys electronics equipment, but a lot of manufacturers will just sometimes use just a tiny little nut and a PCB spacer, which is just a pain to use, just not much fun. Whereas if you had XLR connectors, you could have the pins that would usually carry hot and cold. Hot could carry your cartridge output, cold could carry the cartridge ground, and then the shield and the third pin could carry the turntable ground. So you'd only need 2 XLR connectors to hook your turntable up, which would be a lot nicer really, wouldn't it? Anyway, I think I've probably rattled on about this for long enough. If you've watched this video for this long, then you're to be commended. If there's anything else that you would like me to talk about, I really want to get into the habit of making these videos and improving my presentational style, which I'm sure is not very good. Please do let me know in the comments, and I will actually respond to you. There are loads of things that I want to talk about, and lots of things that you really don't hear about very often, like why passive RIA equalization isn't a very good idea, and various other interesting things. I also really want to start testing electrical components and dispelling some myths regarding semiconductors and capacitors and things like that. So definitely, if you think that there's something that I should talk about, let me know, and I will do my best to do something about it. Alright then, we're nearly at 15 minutes. Thank you for watching.